Hello friends, good evening. Today we are going to see the PMSM motor control and the comparison of Sine PWM technique and field oriented control technique. So this is the Sine PWM based PMSM motor control, and this is the reference speed, and actual speed will be compared with the reference speed and given to the PI controller. And PI controller output will be the modulus index. And this is the Sine PWM generation. I'm generating three sine reference signals using the from the feedback of theta and using trigonometric function, and it's going to generate sine reference wave. And to generate a 120-degree reference signal, I'm going to add 120 degree in terms of omega, the theta value, and with that theta I'm going to generate a 120-degree sine reference signal. So same like that, I'm going to generate a 240-degree sine reference wave, and it will be multiplied with the output of PID controller in terms of modulus index. So these three reference signals will be compared with the triangular waveform to generate a 6 PWM signals. It's going to the inverter. So first I'm setting 1000 RPM. So it's settling at 1000 RPM. I'm going to set 2000 RPM. Here from the motor, I'm taking two outputs. The one is speed value, and it will come in terms of radians per second. I'm converting this into RPM, and the next feedback is rotor angle. Rotor angle will come in terms of radians, and then I'm converting to radians per second by multiplying number of volts. So these theta will go to the sine reference angle generation. So now let me check that speed. So see here, the 2000 it's not reaching. So the maximum speed we can achieve is 1950. So which means here the PID output, which means modulus index is reached the maximum value 1. So we can't go beyond 2000 RPM in Sine PWM techniques. So if we go to the field oriented control technique, we can reach the maximum RPM beyond 2000 or 2500, 3000, anything by adjusting the flux value. That is flux weakening method. So let me open field oriented control. So in this field oriented control, I'm calculating ID and IQ value. I'm going to use PI for each ID and IQ control to control the flux and torque. The ID IQ value will be proportional to flux and torque value. ID will be the flux value, IQ will be proportional to torque value. So next to the speed PI controller, I'm going to use a IQ control, and the output of IQ control will be VQ value. So I'm setting that flux reference value as 0, and I'm comparing with the actual ID value, and PID controller is used. That output of PID controller ID PI controller will be VD value. So then VD and VQ will be converted into VA VBC, and theta will be taken from the motor feedback. That ABC value will be compared with the PWM generator, and in between that PWM generator and the DQ to ABC value, I have used space vector modulation technique. This is min max based minimum maximum value based space vector modulation generation. So I'm setting first. Let me set 2000 RPM. Why do we need to go with a field oriented control, and what is the advantage between the Sine PWM and field oriented control is we can achieve maximum speed by adjusting the flex reference value, by using flex weakening method, and the main important thing is efficiency of the system. So let me check the speed value. The same like that, it's not reaching 2000. So now I'm going to adjust the flex value. So this is flex weakening method. I'm changing the flex value. Usually the flex value will be 0. So by adjusting the flex, by weakening the flex, we reach the 2000 rpm. But if you go with a Sine PWM technique, there is no option to increase the speed beyond the maximum speed. That is the only option. We have to increase the input voltage for the maximum modulus index. So if you are considering with a battery operated EV system, how to increase the battery voltage? So that is not possible. So if you want to increase the input voltage, battery voltage, or input voltage to the inverter, we have to go with a more number of batteries. So if you go with a field oriented control, so we can increase the speed beyond the maximum speed by doing field weakening method without increasing the batteries. So now it's reached 2000 rpm. Let me check with the 2500 rpm. It increased beyond 2000 rpm, but it's not reached 2500. It reached only 2200. So to achieve that 2500 rpm, still we have to adjust the flex value. This is manually adjustment. So next to this field oriented control, maximum torque per ampere control is there. That is MTPA control, and by using that we can adjust the flex automatically. It will decide the flex value. So that we will see in the next video. See, now it's reached 2500 rpm. So this is the flex output. So what I'm setting, -40, the actual flex value is reaching to -40 by using PI controller. So actually here I'm reading the motor feedback current, R phase, Y phase, B phase current, and converting into D and Q value by using ABC to DQ block. That is nothing but Park transformation and Clark transformation. So it will give the ID and IQ value, and it's going to the PID controller to reach the reference value to control the feedback value. Okay, that's it. Thank you. We'll see that MTPA control, how to implement that MTPA control, and how to adjust this flex automatically. We'll see in the next video. Thank you.